Actually, the talk that Mark gave before this one is provide a nice sort of link between what they are doing and what we have done. In particular, I would like to remind you that when you run a medicinal chemistry program or project, it is of course a paramount importance to know all the literature data that has been published. And of course, if you are a sort of big pharma, as we were before Aptuit, we were part of GSK, you have a lot of legacy data that you have generated in-house. But when you become a CRO, all the data that you have generated in-house has gone, so you have really to find all the data that are published in order to complement the information that the clients may be provided to you. So, of course, to be also cost effective, you have to explore source of data for structure that are available for free. And just to mention, for example, the Chemo projects or the Drug Bank, the BindingDB, the PubChem or ChemSpider are all source of public available structures, sometimes structure related to data like Kimball. But of course, there are also a lot of products that are commercially available, like Crossfire or Arius Science, that provide a lot of data linked to structures. But we have to realize that the majority of data are still available on paper, and a lot of data are available on patents. And as Mark was mentioning, usually patents are 2-3 years ahead of publication. So about 1 year ago, 1.5 years ago, in Aptuit, we decided to embark in a process that would allow to extract information, particular information from patents. We did in a sort of niche environment, so focus on particular program and project, not as a wide project to cover all the patents that are available in literature. And we rely mostly on Chemaxon document to structure software, as a lot of structures are encoded as a text. So I will talk through a sort of real case study, so it will make clear what the process that we are putting in place is. As I mentioned, we rely mostly on Chemaxon MolConvert extraction. On top of this, we compiled the Igor Filipov OSRA 2.0, so the two tools complement nicely, so we were able to extract from names and also from the graphic of structures. This case example is a typical request from medicinal chemistry, so the medicinal chemistry come to you as a computational cheminformatician, and they said, have these 23 patents and, that are relevant for my program, in this case, orexin, and they want to extract all the relevant information there, and they want you to build a model, and they want to search pharmac for these kind of things. So we had also some patent in Japanese. For those, we rely on the patent that we get converted from Google, which has a lot of patent also available and also translated in English. So this is a simple exercise that we did. We start from 23 patent. We just run this MolConvert, and at the end we end up with about 30,000 structures. And you see how those are split amongst the keyword, like a structure that came from peptides or from conventional names. In particular, the red one are the one recognized by optical recognition. And this, of course, gives, because in the patents, the draw structures are probably the more relevant, it also provides a sort of hints of where your relevant space in, for example, in log P or molecular weight rely, because probably the draw structure also are the sort of the key one. And of course, there is, we knew that amongst those structures, there is an awful amount of noise and rubbish structure that are not relevant. So usually the common approach would be to sort of run Markush-based substructures into those databases and extract just the relevant structure. But we want to put in place a process that was somehow sustainable, unsupervised, automatable. So instead of using this approach, we tried, if possible, to remove all the junk from the structure that we got from patents. So, and there are very simple filters that you can apply. So just if you remove all the structure that have molecular weight equals 0, that are, for example, all definition by halogen, alkyl, aryl, you remove, in this case, about 3,000 molecules. If you remove all structure that contain atoms that other than this one, of course, you can customize by your own needs. You remove another 6K entry in our example. And if you remove also something that do not contain carbon atoms, you also do remove quite a lot of structure. So if you do an AND or those filter, you remove about 18,000 structure from the initial 30,001. So what you end up in the end with a sort of reduced set of structure from the patents, and what we somehow map those. In this case, you see, for example, the number of counts of each structure amongst each patent, a single patent. So you see that inside some patent, there are structures that are present like 30, 100 times. And these, of course, are kind of fragments or sort of junk that we are not interested in. And then, of course, you see that if you look to the structure that have a sort of number of heavy atoms that are somehow consistent with the size of the molecule, you are interested in the orexin, and also that are not too much frequent in the patent, which means that probably if they were too much frequent in the patent, they could be standards or some sort of reagents, sort of things. We start to identify the sort of key relevant space of orexin compound in our case. So we also use a sort of simple, the color code in this slide is based on number of fragments. So basically, we add a sort of index of complexity. We measure all the fragments between 1 to 7 atom lengths. And in this way, we sort of map the complexity of the structure within the patent. And we were somehow able to identify where the relevant structures could be. So adding to the previous filter, the simple one, the fact that we want molecule with more than 130 fragments from 1 to 7, the number of heavy atoms greater than 22, and the number of duplicates within a single patent less or equal to 3, we end up with about 1,200 structures, unique structures, and about 2,000 non-unique structures. At this point, we ask ourselves, did we get the relevant structure from the patent? And so we did a little bit of retrospective analysis, and we went and looked all the structure that were at the end of the process for each patent. And we saw that, for example, from some patent we extract, for some patent we extract an awful amount of relevant structures, and for some we extract less structure. And this, of course, can be that particular patent contain, that they exemplify a lot of structures, or that there are problems like optical character recognition, or the patent was, the quality of the PDF was sort of not with the quality to be recognized properly. And the bottleneck is both of all this issue together. One particular issue, for example, if we look at that particular patent that has a lot of low throughput of relevant structures, and of course we realize that, for example, these structures from the patent was not recognized, and this structure, which is exactly very, very, very similar, was recognized. And then if you look to the reason for this one not being recognized and that one being recognized is most likely to be the optical character recognition, because many times, for example, in this case, ones and R and L get confused, and then the Chemaxon software is not able to recognize the chemical name, and the structures get not convert. So once we had all this structure, of course, you can do, for example, in our approach, we convert all the structure from 2D and on 3D. In this case, we rely on OpenEye software. So we build a 3D version of the relevant orexin patents, and then we could apply pharmacophore search. So we developed pharmacophore for orexin 1 and orexin 2. So we search the three-dimensional database. We annotate back all the RMS fit with the pharmacophore back to the original data, and then we prepare very simple layouts in instant GenChem, and this is what the medicinal chemistry has as a result, with also some physical chemical properties. So the medicinal chemistry now are in the position to look at the sort of relevant structure from the patent that can match against the model they are aware of or they knew, like a pharmacophore or shape or all this sort of thing. So this is becoming a sort of tools that we release to the medicinal chemistry for sort of patent informatics, if you like, to some extent. What, of course, is more challenging, and of course, we also tackle, although it's not completely automated at the moment, is that for some patent there are tables with the data, and of course the chemists want to generate this sort of graphics where from the patent you get all the compound with the structures, and then you have like the activity on the orexin 1 and orexin 2, and you can pick up the compound that are selective and then really exploit to the maximum the potential of data contained in patent. It is possible, of course, because you can somehow translate all this structure into all this name from the example into structures, and then you can, with some difficulty, with a little bit of Perl scripting or Oak scripting even, to extract the text and then take the column, the second column, the third column, and relate this example to the structure. But in the end, in a process that is not yet fully automated, at least we were not able to complete automated, you can extract also, we were able to extract also the information to produce this data for some patent. This in the end is a process that we are now using in Aptuit. So for this particular aspect, so initially the medicinal chemists collect the relevant document, the relevant patent, using their standard tools, literature tools like SheFinder. And then basically we keep also a Kimball version in Instant GenChem in-house, so they can search whether there are already the data, for example, in Kimball, without having to extract from the patents. And then basically we try to keep the strategic patents. And then basically we follow two processes. One is the fully automated one, which just run overnight in an hour or so. You can extract all the information, apply all the filter, and end up with a bunch of SD file that you can upload in Instant GenChem. This is a full automation. And then for the patent that contain also the table, we can start this sort of pseudo automatic process and the structures and the table and the data from the table. And then in the end, we sort of aggregate in an Instant GenChem database all these two patents, and then we can apply now either release to the medicinal chemistry within the Instant GenChem small data project database, or we use as computational chemists to run a search for pharmacophore or all the other activity that you can do with these structures. Of course, everybody is aware that we are talking about sort of soft information. There might be some sort of error, and people is well aware that those structures come from patents. So we need to and sometimes all the data could be also, we are not 100% sure that this process collect all the relevant data, and some structures that are not relevant could still remain within the process, of course. So in the end, just to come to the conclusion, So the combination of Chemaxon document to structure and the Philip of OSRA to us seems to be a sort of appropriate or sort of handleable process that allow us to extract information from document and in particular from patents. And this somehow allow us to extract information that are not accessible yet to database like Kimball or even commercially available database. This process, because it's a sort of very niche and curated, the patent are the one that medicinal chemists are interested in, so it allows a certain level of control compared to a sort of massive extraction of data from a big a million database of patents. So there is a little bit more curation in handling a smaller number of patents. Of course, there are still a little bit of work in progress, in particular for the extraction of the data from the table and the annotation of this data with the structures. And of course, there is still some issue related to optical character recognition. So I was talking with Roger Say the other day, and he was suggesting, for example, that instead of taking the patent from the micro patents, I could take the patent from the Google one. That's at least for the US patent, they have already a process of character recognition. Also, the image are in a raster format instead of a vectorial format, and there is a better recognition from OSR. So this is a sort of suggestion and things that's probably we need to continue to and is part of work in progress. Of course, it is still a challenge to extract those data from the table, and this, of course, represents the sort of challenge, but also Mark in the previous talk has mentioned this. Also, I was having a chat with the guys from Linguamatics, and also they seems to, with their tools being sort of gone one or two steps ahead in this direction. This maybe could be another sort of integration or possibility to work in the direction. And I think this is my last slide. And if there's any question, I'm here, or just catch me during the breaks.
Thank you. It's a very interesting talk. I have one or two comments, and then I will have a question. So you mentioned the issue with OCR errors, and obviously that's something I know a lot about. It would be very interesting to see in this case what happened. So you just mentioned the case of L being recognized as a 1 or opposite. This kind of error should be automatically fixed. So it might be another one, and that's why I would be interested to see it. I think I will mention some things in the next talk, so I won't go into that. My question is about this color coding that you mentioned. The unicity, is that inside the specific structure, or is it compared to other structures in the same patent?
No, I mean, we count the frequency of the structure within the same patent. And we assume that if a structure is present many times, too much times within the same patent, probably is not a relevant structure, because the important structure will be reported just one or twice in a patent. The structure with the one that's are reported many times, other are reagents, or they are like standard that are mentioned many times.
Yes, I understand, but there is this color coding with the 1 to 7 atoms. And you said that you count how many times it's...
No, the color coding is based on so we for each structure we count all it is based on a in-house code that is more or less doing the fingerprinting. So you measure all the unique path of atoms from 1 to 7 lengths from each atom. So. And this gives a sort of index of complexity of a molecule, and also the unsymmetry or the simplicity. So if a molecule is too simple or too much complex, you have an idea. And of course, this is sort of a little bit target specific, because you are looking for orexin molecule. You know more or less that the complexity and the sort of that molecule is within a certain range. But on top of that, it helps you to remove all the too simple molecules that usually are reagent or sort of small fragments, and combined with the other filter that we've applied, it seems to kind of identify a little bit the relevant air and to remove all the junk from the patents.
Okay, thank you very much.
I saw that you mentioned OSRA before. Mark said they're using Glide. There are some publications pointing out that they use ensemble OCR tools with a much better output. You ever think about this?
No, actually, the reason for using OSRA is that it is free, so I could download, compile, and also get recognized from a molconvert. So there is like an environment variable whether you want or you don't want to use. So I haven't really explored the alternative to OSRA, to be honest. This was just sort of compiled and use it, but I think that's also that area is an area that should be explored.